It should be another draft science video presentation. A little disappointed. Yesterday's video on the two slit, got less than usual views, and I would argue it gets right to the core of this whole the reason why I make these videos. Physics and its silly Heisenberg principle. Like I said, they've made it into a law. They claim they know this is all some sort of probability equation, that there's some sort of innate randomness in the universe, some capacity anyway to obey mathematical rules without any structure to create those rules, that just somehow it knows that if it rolls one this time, the dice, that somehow the dice know they can't do one right away. They have to do some other numbers in between and then do one again. A certain number of times they get to do number one. Well, snake eyes, let's say, with two dice. It really comes down to something that that obvious, is that they've taken physics and decided that because, like I said, the dice bounce a lot, therefore I can say that the dice were never in any position. They never really hit any surface. They never really did anything, that obeys any rules. And that simple explanation that, yes, that's what they're doing. They're just obeying the rules. Explains it, and you don't need to create this fake-averse. So this video is a Sean Carroll video, 2013, but it's the same. He's even worse now in terms of the nonsense of what he claims to be somehow demonstrated by something, like somehow they've proven. Never really shows any evidence. He just claims we know, we found the Higgs boson, we did this, we did that. Anyway, so the funny thing, the irony is that everything he's saying is fits exactly what Ken Wheeler is saying, essentially, about the universe in some respects. In the respect that it's all about some notion of what a field is doing, what the ether is doing, rather than some notion that that stuff actually came from somewhere, and that I've tried to provide you people with reasonable ways to see it, but it's just like light. So that light comes from a source. If you're getting hit by light, you don't sit there and say, well, how much light is right around me here, is coming right. What does the field say? The light field. No, you look at the window where the light's coming in, or you look at the light bulb over there and you say, that's where the light's coming from. I can know that it diminishes with distance because it's spreading. The little bits that it's shooting at me, get less and less the further away I go, because I'm creating more space for those little bits to have to fill. And gravity's doing exactly the same thing. You just think of it in an inverse way. You could sit in a dark room, and then you could turn on a light, and then you could imagine that if the light pulled you towards, it was a tractor beam. So whatever the light was on, there was a tractor beam, and it pulled you instead of pushed it against you or hit you. It'd be perfectly obvious that it doesn't have anything to do with the stupid field. The field isn't making a light. The light's coming from a source. The change is coming from a source. And the fact is if the tractor beam is far enough away, the other spaceship that's trying to pull me in is far enough away, it's going to take real time for its beam, its device, it's changing the field, by shooting something into it or not shooting something into it, creating a void. It's going to take time for that to reach me, just like it's going to take time for ink to get from one side of a bottle to the other side of a bottle. It's going to take time for this stuff to happen. And we can all understand that. We don't need any idea of some bent geodesic or some, space did it. No, space didn't do it. Real sources did it. And that's true of gravity, and that's true of light, and it's true of a magnet, and that's the world we live in. These are real things that change the real universe. So he's going to say things about magnetism right here to start with, like they know how magnets work, and they don't have any clue at all. And so that's just one of his statements he makes. He just makes statements. He doesn't demonstrate them with, even proposing that I go to some link where they'll give me this really brilliant explanation of exactly how a magnet works, which he can't provide. Which just makes the conversation a bit ironic or silly. Both maybe. Ironically silly. Well, that's good enough. It'll do. Let's see, I could probably move this over a little bit. Yes, you probably could. Alright, so as I've pointed out, let's just do the magnet thing real quick just for fun. And just illustrate the place where it all goes south from my perspective. Now, if we put an electron here, so this is the north side of the magnet, and this is the south side, and so you could draw a diagram of what would happen if I put something like, let's say, an electron in this field. Well, we know the electron is going to be repulsive, so the electron is going to move out. And if I put it over here, it's going to move out this way. Well, it's going to move out this way, actually, because it's going to start getting pulled by this other object. So if I have it here, its motion's going to get changed even more. It's repelled by the north side, attracted by the south side. So I could draw an image for what an electron is going to do, and it would have a line something like that, right? Well, we have a line something like this. Okay, it'd go out to infinity as it being pushed away. And so the truth is now if I was to do the same thing with a proton, I'd have two lines, and you could understand how those two lines would essentially combine to create this traditional line of magnetism. And so it's made out of that function, okay, that one end's repelling protons, one end's repelling electrons, and vice versa for the attraction. So they keep drawing it as if there's an actual thing that moves from here, goes all the way around, comes back in here. And they put these little arrows on it, and they say, hey, look, there's something moving here. And that's a Ken Wheeler notion. That's the Distinti guy thinks there's all these currents. All these people think there's some sort of thing, that somehow knows how to move in those directions. Now, if I put a compass needle here, the compass needle doesn't move, doesn't go anywhere. So that's not true. That you're not going to prove it with compass needles, that's for sure. And you're not even going to prove it with an electron, because the electron will move, but it'll obviously move out, okay, away from the north end more than the south end can pull it from that direction, so it won't do anything like this. Okay, the only way this happens is because there is, okay, for every push away by the north side on the electron, it's pulling on the other side of the magnet, the little yellow end. Okay, so this is just how magnets line up. So if I put magnets in this field, they'll line up, and they'll create a path, but it's not a path anything's moving on. So again, there's no experiment in the history of mankind that demonstrates anything moves on any of these lines, that anything's swirling. Nothing. There's no indication of any momentum in a direction. It's just an illustration of what magnets do. Dipoles. A dipole meets a dipole, that's what it does. If they're monopoles, then they're going to move out. Well, the simple argument is that when Maxwell drew charges, he drew charges correctly, he got all that right. And the idea would be is if I have an electron, you can probably see that okay, right? Oh, gee. Lots of glare here. Yeah, that's stupid damn glare. Alright, well, hopefully you saw enough of that. The idea is that the charge is just emanating a force. And you can measure its charge just by saying how far away are you from it, and that's the push force with another electron. And so it's just these straight lines. And that's all there is. And that's all this magnet's doing. It's just making straight lines of repulsive electron force at one end, okay, and proton force at the other end. So if I had the capacity to take a little charge, even 100,000 volts of electricity or something. And I was to put it on a little round sphere, and I put another little round sphere that has 100,000 volts of negative, and I was able to put those right on top of each other, okay, without a spark gapping. The fact is, I'd have something behave exactly like a magnet. You do exactly the same thing, and these are charges. Everybody knows this is what the charges are doing. Okay, it's electron repulsion here, and it's all proton repulsion at the other end, and vice versa for the attraction. It would do exactly the same thing. Now, do you really think there's a flow going from the electron? There's a flow of something going from the electron to the proton, around the outside? No, it's doing this. And that's what creates the R squared rules and the R cubed rule and the R rule that run electricity and magnetism. All those rules are created by how much you're mixing these forces. When they're dipoles, you're going to mix a lot of them, so it's not going to be as effective at a distance. Where the charges are pure, there's no yellow in there, so there's nothing to dilute the repulsion, and so you end up with an R rule, an R rule. The R cubed rules for the dipoles. Anyway, the simple explanation, okay? No fancy mechanics. And where is this force coming from? See, they don't explain any of these forces. They don't explain the thing that's moving. Okay, they don't explain what's going around the magnet, and they don't explain what's pushing it or what's holding it in. What kind of gravity force is making this thing that's going around and around and around. They don't explain either the thing or how the thing is kept in the orbit. So neither one of those are explained. Where this simply explains it as, yes, it's the same energy that's in the universe, the cosmic background radiation. There's radiation around us all the time, tons and tons and tons of little quanta of energy. And it's the energy of gravity that's out there all the time, and it comes in two forms, okay? Proton and electron repulsive force, yellow and blue, or however you want to look, green. And it's all it's doing, simply. That is really irritating. Alright, anyway, all it's doing is filtering it. Comes in mixed, comes out purified. Filtered, simply put. The magnet's just a filter. Filters whatever comes in, comes out a little different. It has an equilibrium with the universe. The universe hits it with stuff, and so it's just like having a mechanism, like a light bulb or something, that all the white light comes into it, and it shoots red light out one end and blue light out the other end. Anyway, not complicated. There's rational explanations, and ones that don't leave a ton of loose ends. A bunch of, again, they have no explanation for, they believe something's moving around the magnet. They can't tell you what it is that's moving, and they can't tell you what's controlling how it's moving. At all. Nothing. Not even close to any kind of explanation. What the hell's going on here? Anyway.
They said the following. I see miracles all around me. Stop and look. It's all astounding. Water, air, fire, and dirt. Gosh darn magnets. How do they work? That's not the actual word. You can Google the word that they said. And they went on and saying, gosh darn scientists you don't know anything. So the scientists... And
it's the truth. And you ought to just admit it. Your evidence is terrible, and your model is a mess. I mean, it's this convoluted mush of, again, bringing back things that we already demonstrated don't exist. This idea of some randomness, or that's little things, the little bits have these ESP powers. They're entangled. Oh, this is a religion. This isn't science. It's horrible nonsense. It's such extraordinary claims, and it's such below ordinary evidence for any of it. And you people are so dishonest that you just can't admit that. You're way past where your evidence can lead you. Way, way past. You have the cart is so far ahead of the horses that, the horses don't even know that we're pulling a cart.
They thought about this because their playlist naturally came up with the Insane Clown Posse. And they were puzzled because they were like, guys, magnets, it's part of our wheelhouse there, magnets.
Part of their wheelhouse. So he says it. He says it's part of our wheelhouse. They call it a virtual photon. They are so clueless. They can't explain it. They can't explain how something that seems to be radiating from the magnet makes attraction. It's like a tractor beam, I mean, they have nothing. They have zero. They have no clue how the magnet works. Nothing. Show me anybody who says they do have a clue. Show me. All right? Point me to the paper. Point me to the video. Point me to the explanation of how magnets work. Okay, go ahead. Make my day.
Kind of do understand how magnets work. So what I want to do, it's true. We do actually understand magnets.
So he said it 3 times. We do. I promise. Go listen to the Richard Feynman explanation. It's brilliant. 5 minutes talking about fat ladies breaking their hip on the ice. I mean, isn't that how magnets work? Shit.
There are things we don't understand. Magnets, not the first thing to choose.
They're so arrogant, so this bravado or whatever. I mean, it's just such hyperbole. We got it. They don't have a clue. It's one of the biggest holes in their whole theory is of how vacuous they are on the subject. They have some rough idea that little magnets are made inside of atoms somehow, but atoms aren't. They don't have monopoles. There's no magnetic monopoles. They even say that. There's no magnetic monopoles. There's no north or south thing. Okay? There isn't. That's how clueless they are. They haven't even figured out that that's kind of a stupid thing to say, because obviously if you're making a dipole, it has to be made out of something. Amazing.
But I want to nevertheless give some points to our plucky duo, because even though we understand how magnets work,
so he said it again. He just says it. We understand. What do you understand? You understand nothing. You can demonstrate nothing. You can show nothing.
It is still true that they are astounding, and we sometimes forget that because we
Well, see, they're really not astounding once you know what they're made out of. It's kind of ho-hum. I mean, it's a simple little filter. Stuff reflects off of it. So the blue stuff just reflects off this end, and the yellow stuff just reflects off that end. And then there's a simple little turn that takes place. Yellow stuff goes in here and it comes out the yellow end, and blue stuff comes in here, it comes out the blue end. Yeah, it's kind of mundane, actually. It's so simple.
Understand how things work. We forget how strange it is, the way that different things work. If you think
all right, so again, that's just evidence of how much they don't know, is that they make it all strange, mysterious, wacky, wonderful, all these kind of words. Oh, nobody can understand quantum mechanics. Well, the reason why you can't understand it is because you have it wrong. Yes, wrong answers are hard to understand. And you have a bunch of wrong perceptions of the reality. I mean, again, just even the dice roll thing, you can understand the dice are actually doing something. They fly through space, they turn, they hit it a certain way because there's a certain length of distance and blah, blah, blah. You can understand that it's just a mechanical process to come up with whatever lands on the dice.
About a magnet. What does a magnet do? A magnet sticks to your refrigerator. But lots of things stick to your refrigerator, right? A piece of tape would stick to your refrigerator. A gecko would stick to your refrigerator. That's not surprising. What's surprising is that the piece of tape, in order to get it to stick to your refrigerator, has to touch the refrigerator.
All right, so you can make these same arguments that charge doesn't need to stick to your refrigerator either. So you can charge something, and so you don't need a magnet. There's other mechanisms that behave exactly the same way, in the sense they'll stick without actually touching. That is, they'll be attracted without actually touching.
That makes sense. It has to sort of cling. There has to be some part of the piece of tape that is interacting with the refrigerator to keep it stuck. But the magnet, if you hold a magnet close to the refrigerator, it starts pulling on the refrigerator. It starts pulling toward there.
So again, this conversation about this idea of pulling, again, not recognizing that it's the same force that's holding the atoms together. Again, the force has to be coming from the outside, you people. It's just so obvious. It's rudimentarily so much simpler than any notion of a pull. There is no pull. There's just an absence of push. You take away the equality of pushing as much on one side as you're pushing on another side, and you can figure out the object's going to have to move. And so all the magnet's doing is it's eliminating force between the object and the magnet, and the magnet's going to stick because there's an absence of force, because the force is being redirected. The force is going somewhere else than reflecting.
Before it actually touches. How does the magnet know that there's a refrigerator nearby that it needs to stick to?
Because like all of us, like every single thing in the universe, it's taking in energy and excreting energy. That's how it knows. Every single thing is connected to every other thing. The light is, how do I know the light's on? Oh, because it's sending photons that are hitting me. That's how I know.
How does the magnet reach across space and say, yes, refrigerator, good, I'm ready for this?
Yeah, let's understand. It reaches across at the same speed as gravity and the same speed as light, and all these phenomenons that are being dictated by these little bits moving the speed of light, that are the force, that are the thing, the carrier of a message. And the message is either I'm providing you with something or I'm not providing. I'm blocking it or I'm sending it. The light is on or the light is off. The light has been turned, right? I had turned the light to look at you, or I can turn the light and it's pointing somewhere else. If it's pointing somewhere else, then you have a void of light here. And if there was another light on the other side, then you'd get the idea that one light's pushing me and the other light's not here right now because it's doing this. It's pointing in a different direction. So I'm going to have an imbalance, and I'm going to move in the imbalance. The absence is going to be felt, okay, because it's a real thing. It's a real absence.
I got this. How do they work? That is a very respectable question. It's not only Violent J and Shaggy 2 Dope who want to know, it's this guy, Isaac Newton. Isaac Newton, very famous for inventing gravity. He didn't invent gravity, it's been around for a long time, but he invented the law of gravity that really works.
So, he invented, he discovered the simple relationship that just like a light bulb, that's how gravity's working. Just invert the principle, it's doing exactly the same thing that light's doing. And that's how it's functioning. It's like a negative light bulb.
It's not the perfect law because Einstein came up with an even better one.
So again, it says this is more statement. Okay, Einstein came up with a better one. It's really not a better one. That's why no one ever uses it. And, it could take you years to figure out an answer that Newton will let you understand in a few minutes, seconds even. You need supercomputers, to use the Einstein approximation. And they're all going to be approximations because there's certain rules to the math even working, and that has to do with spherical symmetry. So if I make the object a little less than perfectly spherical, I'm going to change the equation. Now, it's usually not enough to matter, so nobody pays any attention, but it's a real fact.
But Newton's version of gravity is good enough to get you to the moon, for example. And it was a very simple idea. His idea was that gravity was universal, and that it obeys a certain very simple mathematical relationship. Here's the Earth, here's some objects, some satellites that NASA has built.
So you could just simply describe that as there's a body that creates a certain amount of change in the universe. So it's if it was, you just think of, again, if it was a light bulb and the light makes you move towards it. So you think of the blue object as being, well, the more massive it is, the more light it creates, the more light it produces. And obviously the closer I am to the light, the more light that hits me. And it's exactly the same inverse square law. You could write a light equation that looks just like Newton's gravity equation. It's the same concept. It's about objects and how they change the universe around them by excreting something real, a real change in the stuff, and the fact that it moves at a time means simply that it's a real thing that's moving. It's not some sort of bent magic. It's obviously something not magical, but it has to take time to get from one place to another.
Flying around the Earth, and Newton says there's a gravitational pull on every object that is proportional to the mass of the object pulling it, which makes sense, but also it gets fainter and fainter the further you go away as the distance squared.
And again, the same law, that same understanding applies to most all of these circumstances, because they all have to do with things radiating. And the idea is that you get the message pretty clearly when you understand that the two things are opposite, and that's why they mix in the dipole. The magnetic dipole is mixing the two things. It's saying come and it's saying leave. And those two things start mixing. You start getting some of each, a little bit of no light and then extra light from the other side, that it ends up being half of the force that it was, and therefore it's going to be an r cubed rule instead of an r squared rule.
Inverse square law. The bigger the distance, the weaker the force. And that simple idea, the force of gravity goes as 1 over the distance squared, works for apples falling from trees, works for the moon going around the Earth, it works for stars going around the Milky Way. It's incredible.
And it works for a light bulb.
Incredibly effective. The problem was, from the 17th century point of view, when Newton was thinking of this, it made no sense. Newtonian gravity in Newton's day was a...
So again, it does make sense, and Newton considered the making sense argument of Faddeo's gravity, the idea that it's an external pressure. And the only problem they came up with is, first they had to deal with the fact that it does take time for this gravity to send its signals. And so in the case of gravity, you'd have to understand that there's a huge time delay in position versus where the gravity could possibly be sent back. So you have to understand that there has to be some other mechanism that stores this light, so this light can keep shining in all directions, not just the direction you are in. And this drag argument, and the drag argument was a significant one, but they should have known it's not catastrophic, because all they have to do is think about this as a nuclear function, and that the nuclear bits are behaving subtly different rules than big objects. The two things aren't exactly the same. We live in a world where friction is everywhere. On the nuclear scale, there's no sign of it anywhere.
A lot like quantum mechanics is to us today. It's a theory that fits the data beautifully. It's obviously right.
So here we go. Theory that fits the data is obviously right, blah, blah, blah. That's how they're just so trite about this obligation to actually prove a case. All they're doing is walking into court and saying, he looks like a murderer, doesn't he? I mean, look at him. I mean, how can you doubt it? It's just so obvious. He's a murderer. Evidence? No, we don't need that.
But there's a part of it that doesn't really make intuitive sense to us. For Newton, it was this action.
So again, it always made sense to me, because I always knew there was some kind of mechanism. There was a something that was telling the little bits they had to move. They didn't just say, I'm sensing a geodesic, and the geodesic is telling me I have to move, even though it's invisible and it's nothing. There was always in my brain a something. Something makes things move. Nothing doesn't make things move. And that's their physics. Because we can't figure it out, we're just going to say nothing did it. They're going to make it magic.
Aspect of action at a distance. So you're over here, you're this guy, you want to know, what is the gravitational field pulling me right or left or whatever? What is the force on me due to gravity? And Newton says, all you have to do to figure out the force due to gravity is take every object in the entire universe, figure out how far away it is, how much mass it is, and apply the inverse square law.
Well, and that's the truth of it, right? You want to know what light's hitting you, you have to know all the sources of the light. That's just your obligation, okay? There's one over there, there's one over there, there's one over there. That's the only way I can know what's going to affect me. Now, I could sample the entire world all around me, any one moment I could just sample this piece of space all around me. And yeah, that'll give me the answer too, but frankly, there's no way to sample that. So what good is that going to do me? Is that going to answer the question? No, and I already know the light's on its way. So yeah, I know if I sample how much light is hitting right over here, right here. If I know how much light is hitting my hand right here, then I can know how much light's going to hit me when that hand's not in the way. I mean, because I know where the source is. So I'm still dependent on the source and testing it, So knowing it versus testing it, there's no conflict in these two arguments. Newton could figure this out. Newton could have said something silly like, well, draw a circle around one of those little dots, right? Just draw a big circle around it. And then test what the field is in all those locations. And that'll tell you how much force is going to affect the thing inside the circle. Of course. Duh. The light has to go through that imaginary circle I make to get to me. So obviously, I can detect how much light is going to penetrate it. I can make a big bubble, a plastic bubble. And I can use the bubble to say how much light is there hitting the surface of the bubble, and then I can tell how much light's going to hit me. Duh.
And people said, that seems strange that I need to understand every object in the universe to figure out what the gravitational force is on me right here. Why? That seems spooky. It's action at a distance.
Okay, so again, that's just silly, right? There's no action at a distance. Newton was saying things move, okay, at great distances. And there's the action at a distance is the word action. There's action. Something's happening, and it's happening because the light exists. So if you thought about the light as being attractive, or even if you thought about it as it is being repulsive, and just thought of it as a pushing thing, okay, yeah, it's pushing me from a distance. But again, if you understand it as just being bits of stuff hitting you, well, obviously it's going to push you. That's what it's doing. It's throwing things at you. You're going to move because of the things it threw at you. Now, if you understand that the light really is a shadow, that's where energy has been being absorbed and being eliminated from hitting you, well, then that's gravity.
Like something going on in the Andromeda Galaxy is affecting me right here, right now. And Newton was...
So again, it's not right here, right now. Because just like light, it takes it, hundreds of thousands of years or millions of years or billions of light years to actually create the effect. Andromeda, whatever it is, how many light years is it? 10, 20, whatever. That's how many light years it takes for any position it's in for you to know it's in that position and it blocked energy as it was moving. But the key to it is, again, the energy it's blocking is going to create an effect that goes in all directions. If I want to counter something going this way, I can counter it. If some force is pushing on an object and the force pushes this way or it pushes this way and it pushes this way. Now obviously this way is going to equal this. And this way is going to equal a little bit of that because it has a component in this direction. So if I want to make pressure, I can hit things at angles, all kinds of angles. All right, and so you can sort of understand that if I want to equalize a pressure, that is, a pressure came in this way, I can equalize it by doing 3 of these. 3 reflections on the other side will equal a straight-on hit this way. So I can create a counterbalance. I can rebalance a system by sending back in all directions something that comes in this direction.
Very, very bugged by this. He says this makes no sense. I leave the mechanism for how gravity actually functions to smarter people in future generations. He knew that it was a puzzle.
Well, that's, again, he didn't say that. so we see the smarter part. He knew it was something to be discovered, and he also made a statement about how it would be kind of ludicrous to think nothing does it, that there's just some magic that it makes it happen. So he did sort of add the extra bit, who really thinks there's no mechanism? And here physics has come up with a non-real, vacuous answer of it's just the space that does it. It's just some sort of magical function of space.
So the puzzle actually was resolved, and this guy does not get nearly enough credit, by Pierre-Simon Laplace. in the 18th century. He was a famous physicist and mathematician.
So again, there was no this. Obviously, if everybody would know his name, if it was that brilliant an observation, all he did was draw the inverse square law. So again, I've pointed out that's all Einstein's doing. He's just telling you, well, the inverse square law creates a line. Okay, that's just a fact. It creates a curve. All right, based on the strength of a light bulb, even. Okay, it has a line. You can draw it on a chart. How strong is the light? And the chart line will be a curved line. Okay, light is strong and it gets weaker and weaker and weaker by the inverse square law, and that ends up being a nice little curved line.
And he's famous for telling Napoleon that he didn't need to use God to explain the positions of the planets, which might seem cheeky and very out of character for Laplace, because he was basically a social climber. But his wit got ahead of him that one time. Anyway, long before Napoleon, Laplace was puzzling about this idea of gravity. He was trying to understand the shape of the Earth, the motion of the planets. What he realized is you could take Newton's theory of gravity, the inverse square law. He didn't change the theory. He said you could rewrite the theory.
Right, okay, he didn't change the theory. These are the key words that he'll say something completely different later. Yeah, there's nothing changed. It's just a way of illustrating, but that's it. It's an illustration. It doesn't change the fact, and the whole thing is dependent on some notion that things roll down hills. I mean, it doesn't add any information at all.
By imagining that there is a field filling space. So what is a field? A field is just something that fills space, that takes on a value everywhere. So the temperature of the air in this room is a field. At every point in space, there's a temperature.
Right, and even as temperature, you could understand that the closer you are to the heater, the warmer it's going to get. So if I put a heater in the room, it gets warmer and warmer and warmer. It's sort of progressive. Now, heat is a little more complicated because of, the fact that the molecules end up getting more buoyant as they heat up, and so they start moving in other directions and creating all kinds of currents. So it doesn't do it as cleanly as other things because the force of heat isn't going to move in straight lines because of buoyancy. Like in space, it will. Okay, it'll be a straight line force like all the other forces. So this is, again, just trying to pretend that the field is doing it when the source is doing it. There's always sources. Sources produce the effect, okay? Causes, real things have real effects. And again, the fact that somebody could cast a shadow on me, right? I could stand outside and there could be a big building there and it's casting a shadow on me, stopping the sun from hitting me. Well, the fact that I could say that the shadow has a depth, and I can move closer and closer to the object, and I can make the shadow darker and darker and darker the closer I get because I'm getting less refracted light. There's nothing magical about that. The field didn't do it. The building did it.
Value. But temperature is obviously not fundamental. It's a property of the air. The gravitational field that Laplace is talking about, this is a thing. This is a fundamental ingredient to reality. And Laplace came up with an equation that his gravitational potential field obeyed. And he says that through this equation, he could exactly reproduce all the predictions of Newtonian gravity.
So, and again, and it's completely dependent on something so obvious. Yes, I could just make myself twice as big, okay, and I'll measure a different amount of light hitting my surface because I'm in a different location. I'm changing my location. I change what the field is going to say I'm getting, and then I could mathematically understand that all I have to do is reduce that circumference, and I'll get the same. It's just the circular argument. You make the circle bigger by the diameter, and then you get the whole pi argument that the circumference increases by a much bigger number than the doubling of the diameter, and then you just do the math and you can figure out how much light you've got on the big sphere versus the little sphere. There's nothing here that's a discovery of anything. All of this had already been known long before 1783.
Now, here's the Laplacian picture of how gravity works. Here's the Earth. Here's the gravitational potential field, has a value at every point in space. It's low here, it's higher here. And Laplace says that the force that you feel due to gravity is just the slope of this field. If it's tilting down a lot, gravity is strong. If it's tilting just a little bit, gravity is very, very weak.
Right. The only thing that changes this is you put a lot of bodies in the field, right? A lot of sources of light, and then your slope is going to have some change in it because you have different sources of light, and it's going to bend the slope this way or that way depending on, whether you're being pulled by the other light sources more than this one right next to you, and these others have to be accounted for. They all count, every source, but it's the sources that are causing it. The field has nothing to do with it. The field is irrelevant if you think about the cause just being something that's moving at the speed of light.
Exactly the same experimental predictions as Newton. Why is this better in some sense than Newton? Because
it's nowhere close than better, because there's absolutely no way to calculate that curve without accounting for all the sources. So without, again, measuring every single bit of the surface. I mean, what's the difference? Yes, of course, you'll know exactly how much light is hitting you if you measure the light that's hitting you. Then you'll know how much light's hitting you. Duh. It gives you no mechanism, no way to cheat. You still have to account for all the sources. You either account for them by measuring and detecting them with some way of detecting them from each direction, or you account for them by knowing they exist and just figuring out how many watts it is and then how far away I am. So I either calculate how much light is hitting me from understanding the source and its brightness, or I just measure it. But those are the only two choices. I mean, if there's a candle in the room and you're sitting there, you can either just sit there and measure how much candle light's hitting you, or you can understand how much light it's producing and then just do the calculation of the distance.
To figure out the force due to gravity here, I don't need to know the universe infinitely far away.
Right. Duh. If I detect how much light is hitting me, I can explain how bright the candle is. If I measure how much light is hitting me, I know by the inverse square law exactly how bright the candle is. So if I measure a square foot of space and I measure how many photons hit it, I can do the calculation. It'll tell me exactly how bright the candle is. There's nothing. Newton knew that.
If someone told me what was going on in a sphere around that particle, if someone told me the gravitational potential in some region, that would be enough.
Yeah, it does. So again, he's just saying I can just put a bubble around me and measure every single bit of energy that's hitting that bubble, and then I can just do simple math to figure out how much is hitting me. Duh. Obviously, everything that hits me has to go through the bubble. It can't get to me without going through the bubble. I mean, this is just so unremarkable, so trivial, and again, he's highlighting this is like the Young double slit experiment. After Newton had already done all the surface experiments, outside surfaces, interior surfaces, he's done them all. He's kind of known for the phenomenon, Newton's rings, the same thing as fringes. It's Newton's game, and here some guy comes up, shows up young, does something completely unremarkable, and they make it into something like, well, Young discovered something. No, he didn't. He didn't add any knowledge whatsoever. He added zero information that Newton hadn't already discovered. No fact. There was no fact that Young demonstrated that Newton hadn't already demonstrated.
Once you invent field theory, the laws of physics are not action at a distance. They are local. The information you need is contained nearby you.
All right, so that just think of what he's saying. He's saying, look, you don't have to pay attention to the sources of the light. They're not the game. They're not the players. They're not it's not the ball to watch, is what the sources are. Somehow the ball to watch is some imaginary field you created around yourself. And that somehow is going to help you in some way. And again, it doesn't help in any real way. Again, Newton could have come up with some crap like that. Yes, if I can measure exactly how much energy is hitting my hand, and I can measure how big my hand is, I can tell you exactly how much light is coming from the source.
The mechanism for why gravity works is now explained. It's not instantaneous weird communication over infinite distances.
All right, again, and Newton had no clue whether it was or was not. Okay, he knew the speed of light pretty accurately. But yeah, he didn't know whether gravity was a force moving the same speed or not. There was no way to detect that, so he had made no decision.
Is that the Earth pushes down the field right there, and that pulls the field right there, and that pulls the field right there, and that pulls the field throughout the rest of space.
So again, he's making forces affect forces, which they don't do. Okay, electrons. When an electron bangs off of another electron, the electrons' fields, their fields aren't hitting each other. Now you can imagine, all right, the consequence. Like you can know what's actually going to happen. The two electrons are never going to hit each other. They're going to bounce off each other's field. But the truth is, the fact is that the field from this electron is going to have to actually hit the surface of this electron to move it, to push on it. The two fields won't push on each other. And he's almost implying that somehow we can just measure fields and what they're doing, all right, and that'll give us an understanding of how it functions. When that'll tell you, yes, there's a field there. So if I'm moving this electron, I can say, yeah, there's a field here, and this is a field here, and I can mathematically understand that this object's field will eventually hit this object, and this one will hit this object. But that's exactly what's going to happen. And to say the field is making it happen is just wrong, because the field has to hit the matter. The energy of the light has to actually reach the surface.
Everything touches everything else and communicates to its nearest neighbors, not to the whole rest of the universe.
All right, so he said it, not to the rest of the universe. Of course it ends up being the rest of the universe. The light bulb, the star far away does influence, does create gravity, and it's the star that did it. It's the shadow, okay, in the field that creates an absence that you're going to sense, that you're going to feel as an imbalance. And it's a fact, and it did it. The field didn't do it. The source did it. The thing making the shadow created the shadow.
So that paradigm seemed to be extremely effective. By the 19th century, we had a picture of physics where matter, stuff, was made of particles, atoms. Atoms became sort of accepted by the modern scientific community in the 19th century. And forces, we said, are made of fields. The electromagnetic field was understood in the 19th century.
Yeah, so he says it was understood. They don't understand it. They have some equations that are useful, okay, but the equations don't have the things they say are in them. These properties of being a wave and being this and being, those aren't in the equations. The equations are really just outlining this fact that there's a force created by the objects, that the objects create a field, okay, and you can measure the local effect, or you can understand, well, it's not just local to me, it's local to every place the light goes. Yes, everybody gets hit by the light is going to feel it's personal, but it's not personal from the source.
Century, as well as the gravitational field. The 20th century was more absolutist in its leanings. The 20th century comes along and says, you know what? That particle stuff is overrated. Actually, everything is made of field.
All right, so this is where it all goes, nutty. So they've made an excuse to just measure the light, and now they're saying everything's just light. Everything's just and they don't think the light is actually something. They think the light is just this field intensity, an intensity in a location. Well, I mean, obviously, in a way, that's the truth, in the sense that as the photon's moving through space, it's occupying a piece of space and it's moving in a direction. And so, yes, it's filling space at that location, and then when it's gone, there's nothing in that location again. So, I mean, there's two different states it can be in. It has a photon in it moving in a direction, or it doesn't have a photon in it moving in a direction. That's a truth. But that doesn't give you license to say the field done it.
You don't need to separately talk about matter made of particles and forces made of fields. All you need are...
Right, so forces made of particles and matter made of particles is the rational way to look at it. They're all things, and the things give each other momentum. So the little bits move the speed of light, and they give momentum to the big bits that move much slower. That's the simple explanation, and it works for everything, and you don't need any of this wooey field notions that somehow there's magic in a field somewhere. There's stuff in the universe, and the stuff bangs into other stuff, and it shares, it pushes, simply.
Fields. That should puzzle you a little bit. How can it be? I'm telling you, and I'm not going to back off this later. This podium right in front of me is made of fields.
So again, so this is what you people really believe, that there isn't matter. Okay, there isn't a distinction between the force and the bits that are reacting. Now I could argue that you could turn this all elemental and say, yes, it's all made out of force, and the force is trapped inside of things we call electrons and protons, and they're contained inside of a membrane. And that's the real distinction, just like the plasma, and the blood cell. There's a small distinction between the stuff inside the blood cell and the stuff inside the plasma, and there's this distinction of, that doesn't add up to much, that this membrane is allowing stuff to move in through one, and it be excreted out of the other. There's a certain kind of a parallel there. You could say it's all plasma. It's all kind of some fluid, even, you could argue. It's fluid inside the cell, and there's fluid outside the cell. And this is just a fluid dynamic between this barrier that doesn't allow all the fluid to just freely move. It filters it.
Little vibrating numbers at every point in space are what make up this podium, are what make up me and what make up you.
All right, so it just denies the reality where we have this huge distinction between all these forces moving the speed of light. So all these the stuff that is a force or a field or whatever they want to call it, it's moving the speed of light, and it's a real thing. And we know the matter doesn't move the speed of light, and that you have to hit it with a bunch of force. I mean, as Newton put it clearly, you have to act on it to change its motion. You have to act on it with a real force. You have to turn the light on.
But we feel solid, right? How can it possibly be that something as tangible and solid as ourselves, or the Earth, can be made of vibrations or oscillations or gradients in fields filling space?
All right, just to the Ken Wheeler loop-de-doos, right? So Ken Wheeler keeps saying conventional physics is particle physics and blah, blah, blah. He's saying it right there. He's saying this stupid notion that somehow we're all just vibrations, or we're all just whatever this bullshit is, ether perturbation, and that's all you need. Now you need a lot more than that to make a sensible model.
Well, the answer, of course, is quantum mechanics. Quantum mechanics is what you need, and when you add quantum mechanics to fields, you make quantum field theory. This unhelpful little graphic is just to point out an interesting fact, which is that to working physicists, quantum field theory is the most important thing we know.
Right. So this is the big lie, right? They say we're particle physics, we say we're this, dualities, all this other stuff. He's saying clearly, no, it is waves, it's not particles. And he's saying that, yes, most of us physicists believe that. So don't fall for the idea that we call it particle physics, because we don't believe in any of that.
We learn quantum field theory in graduate school. There are billions of books written about it, from quantum field theory for mathematicians to quantum field theory for dummies. And
they're the same difference.
How is quantum field theory possible? I didn't read that book, but it is possible. It works.
It doesn't work because it denies the fundamental fact that there's sources, okay? The gravity is caused by the stars and the moons and the planets. It's not caused by the field. The real source is identifiable, and to pretend, well, I can know where the sources are, I can tell where a flashlight is because it's pointing at me, I can see it. It's just kind of bullshit to say, oh, it's because I saw the light a foot away from me, okay, therefore I know there's a flashlight over there. Yeah, of course, because the light can't get a foot away from you unless something shot it there. Oh, this is so bad.
The point is that when we talk about physics to non-physicists, when we popularize it, we never mention quantum field theory. We talk about particle physics, we talk about relativity, we talk about quantum mechanics,
Yeah, you just called it quantum mechanics a second ago, but whatever. Yeah, you talk a bunch of nonsense about your fake laws and principles that somehow you proved any of this stuff when you haven't proven any of it. You have nothing. Your evidence sucks. It isn't consistent. The irregularities can be pointed out, and you'll ignore those references. You don't explain simple things. The two-slit experiment in photons creates two patterns. Why does it do that? Electrons don't do that. What's the principle involved? Why does it happen? You have no explanation, and yet you just pretend we've done it. We've got it all figured out.
Heck, we talk about string theory and the multiverse and the entropic principle, but we...
Yeah, and nobody rational does that. It's multiverse. I mean, this is just so bad. I mean, again, if dissidents had theory this unevidenced, right? You'd be mocking them as flat earthers. You know, oh, you're just deniers. Oh, you're just, what do you mean? Oh, you mean you're going to pretend that there isn't a source of the light because I can measure there's photons here? I'm supposed to pretend I don't know it's coming from the frickin' light bulb over there?
think the quantum field theory, yeah, it's too much to bother about. And as a result, no one got it when we discovered the Higgs boson. Because to understand why the Higgs boson is important, you need quantum field theory.
Yeah, whatever. Yeah. And the 400 other idiotic particles you found are important. None of them are important. None of them do anything inside the atom. They don't account for any of the mass inside the atom. They're just bullshit. There's no room for them. We've already identified what's in the atom, and we've already identified what's relevant to the atom.
So let me remind you, in case your quantum mechanics has become a little rusty, what quantum mechanics is all about. The motto of quantum mechanics is that what we see when we look at the universe, what we can observe or measure, is in principle very different from what actually exists out there in the universe. In classical physics, in Newtonian...
Okay, the simple principle is the little universe is small, and it's really hard to see small things. Because the way you see something is to bounce something off of it and see it, see how far away it is. That's really what you're doing, right? You're measuring its distance by throwing something at it, getting it back, and that tells you how far away it is. It provides that piece of information that has that built into it. And so, light provides this great mechanism. It shoots things at it, it comes back to us, and we can actually just see things. But we can't shoot light at a photon. We can't shoot light at these little tiny things, okay? Because they get shot all over the place. You can't get a right reading. So it's like shooting cannonballs at a Volkswagen and saying, gee, I'm going to see where the Volkswagen is. No, because your cannonball is going to move where the Volkswagen is. You're not going to see it. So that's the simple truth. We can't see little things. It's a fact. We don't have the technology. There's no mechanical mechanism that provides a way to do that. They can't be sensed. They can't be tested because they're so small. We have nothing small enough to test them with. That's the simple truth. And instead of just saying that honestly, they say, no, we can't see them because God says we're not allowed to see them. The magic of the universe says they're not allowed to be understood. Their position has got to remain, their non-position has to be non-positional. I mean, it's a religion.
Physics. There was a particle or a field, that's okay. The particle has a position, it has a velocity, the field has a value, and it has a change in time. And if you tried hard enough and worked carefully enough, you could measure any one of those values with as good precision as you could.
You could model them. You can model the rays of light and do it quite accurately as straight line force. And it works. It's really reliable. You don't need to pretend that the photon over here, he could be the photon over here, and the photon over here could be the one over there. They don't really decide who hit you until they hit you. Then they decide what photon hit you. It's a frickin' fable. There's no evidence. There's no need for it. The straight line little theory works just fine. The theory that there's a little bit and it flies through space at a certain speed and it lands at a certain location based on where it was shot from. The bullet explanation fits all the evidence. It works just fine. Okay, accepting the fact that we know we can't tell, we can't shoot the gun straight enough to know, oh, that was a crooked bullet, that was a crooked bullet. So, you just accept the fact that the bullets don't always come out of the gun straight. Simple logical answer. You don't need to create this fake notion that all the bullets didn't know where they are in space.
Possibly want to get. Quantum mechanics says that reality is fundamentally different than that. That there's something going on that you can never see directly. That what you see when you look at the universe is different than what the universe really is. And that bugged people when it was invented, and it continues to bug people.
Yeah, it's stupid. The simple answer is we can't see it for the simple logical reason, again, that there's nothing smaller I can hit it with. There's nothing smaller than a Volkswagen in the universe, right? That there's just no way to see it except to hit it with another Volkswagen. How can I see it if I hit it with something just as big as the Volkswagen? I can't tell where it is. If the only way to measure where a tennis ball was on the tennis court, right? Say they use photons to tell where the tennis ball is, right? They measure its shadow, where it's going, where it is. And but if they didn't have light and all they had was tennis balls, you can understand that I'm not going to be able to tell where the tennis ball is by throwing another tennis ball at it. That I'm going to change where it's going. It's going to have a different end result, and it's just obvious. I don't need a magical theory to understand that. There's nothing smaller. I can't see photons. It just isn't going to happen. Okay, it's just not. I can only see where they came from. And that always works. That math always works. There's no problem just thinking of it as a photon. It has an angular reflection, goes into my eye. Not that it went everywhere in the universe or pretended it went everywhere. You don't need to believe that nonsense.
Well, today. So, for example, a spinning top, it turns out that in quantum mechanics, the allowed values that you can measure of the spin of the top are fixed. There's a fixed set of possible answers you can get when you ask how fast is the top spinning. Now, the minimum possible answer turns out to be a quite small amount of spin. So you're not going to do this experiment. Even Fermilab is never going to do this experiment. If you took this top...
Well, it's a silly analogy because we know tops don't spin, unless they overcome gravity to do it. So this is a stupid argument anyway, because there is a minimum spin that has to be a certain amount of speed. If I spin the top, slow enough where it takes it 1 trillion years to go once around, it's not going to spin. It's going to just fall on the ground. So this is a terrible analogy. So he's just really doing the Planck thing. He's just pointing out how there's a certain Planck distances in the universe. And so there's a minimum amount of distance you can move in a minimum amount of time. So what?
And said, can we rotate it the slowest it is possible to rotate a top? It would turn around once on its axis once every 100 million times the age of the universe. So it's very slow. But if you have an elementary particle, then this discreteness of observable amounts of spin becomes very, very important. That's why quantum mechanics first came into our notice when we started studying elementary particles.
So this is just bullshit. This is just, again, you can make all kinds of theories about why pi exists, okay, in terms of it's a non-resolvable number. And the argument could be made it's a non-resolvable number because it has to be true for every single circle you create. so obviously every single circle is different, and therefore every single circle has a slightly different true value, the absolutely accurate value.
So this feature that certain observable features are quantized is where the word quantum mechanics comes from. And
so again, that's the idea that it's quantized, that it comes in clumps, is clearly the reason why they called it quantum mechanics, because it started off with quantum electrodynamics. That's what it started off with, was this simple relationship between this photon energy, the energy of the electromagnetic spectrum, and electrons. That's what the whole thing started with, is how those two things interact with each other. And then they piled on all of this bullshit.
Quantum mechanics says this idea that there's an electron, a particle, and it has a position and it has a velocity is just wrong.
Okay, so I'll leave there. There's just no point. It's just a religion. It's just, there's just no evidence that it doesn't have a position and it doesn't have a mission statement to go somewhere. And the simple truth is that if you want to know those facts, the facts of its position, you're going to have to mess with its position. You're going to have to hit the Volkswagen with a Volkswagen, and you're not going to get a very accurate description of its position based on how far the Volkswagen bounces back, because it just isn't going to happen that way. For you to get the Volkswagen back, you're going to have to impose so much force that you're going to shoot the thing who knows where. It's not going to you're not going to know where it was going for sure if you know where it was, because you just blew the frig out of it. And if you want to know where it's going, in terms of its destination, well, that means I have to test it by sticking a Volkswagen in front of it. It has to hit the Volkswagen then. I put a dead Volkswagen in front of it, let it plow into it. Well, that's really not going to tell me where it's going, because, again, how am I going to see the Volkswagen's motion when it's going to end up going where the Volkswagen was going? It's not going to come back to me. I'm not going to be able to get the information. So, yeah, the more I try to test one, I lose more relevance to the other. If I want to know the distance, it gets harder and harder to know, the direction. It gets harder to know the position, and vice versa. But that's just logic when you're testing with objects way too big to test with, that are going to influence its direction. It's a simple argument. I mean, again, this is so frustrating, because this is so bad. It's so unevidenced, and for all you dupes and saps to fall for this crap and then be so fucking obnoxiously arrogant in your silly, nonsensical religion. It's just so bad. It's a silly theory. Silly. And there's no reason for it except you want it that way. Clearly. You want the outs that this wacky theory provides, in terms of it just makes everything a little bit mysterious and magical, and then you can self-aggrandize the human race and your functions and everything else into some sort of magical thing that's happening in your magic verse. And that's all it is. It's silly. It's trivially silly. It's so obviously silly as the right answer. It's the wrong answer. And why are you selling it? And then pretending you're smart. Ugh. You're disgusting. Yuck.